I'm Dennis Buckmaster, a professor of Ag and Biological Engineering and a Dean's Fellow for Digital Agriculture, and I want to welcome you to the Agronomy Center for Research and Education. And to give us a good introduction to that, we've got the manager here, Rachel Stevens. She's got degrees in Mechanized Systems Management with a focus in Precision Ag and another degree in Agronomy. So who better to manage a research facility? I don't know. So we're very fortunate to have her. She's a relatively recent hire. But Rachel, could you give us just a good description of what kind of work happens here at Acre?
Absolutely. Yeah, let me give you a little bit of a background on Acre. Again, like Dennis said, this is the Agronomy Center for Research and Education. Acre, the Agronomy Center for Research and Education, was founded in 1949. And originally, a lot of the research that went on around here was a lot of breeding plots. That was kind of the beginning of hybridization of corn. And so that was really a lot of the core research that was done here initially at the beginning of the farm. But since then, we've really expanded what we do out here. Aside from the Department of Agronomy, we have 8 different departments out here at the farm and probably about 100 different researchers conducting a variety of experiments out here. So we have everything from, still some of those same breeding plots that we started with, but also, we do things pertaining to management practices, helping farmers make better educated decisions with some of the data layers that they have. We're doing a lot in the space of digital agriculture. We do a lot in crop protection, testing a variety of products that a farmer would try out on their field eventually. And then we have a lot of other kind of, I would say, ancillary projects going on. So we have grain systems management. We have a wide variety of folks from the environmental and natural resources departments, so doing quite a range of research out here. So a lot going on at the farm. We're about 1,600 acres, and that's a mix of small plot stuff as well as field scale, research that we're doing. So yeah, that's the range of stuff that's going on at the farm. And yeah, so the question was if the 1,600 acres are contiguous, and yes, largely it is. So we kind of stretch here from on 52 up to County Road 500, and then have a few hundred acres on the north side of the county road there, where we butt up against the animal science farm. So.
And for the operation of the farm, do you have your own full-time staff, or how big is that staff?
Correct. So the question was what the staff is like here on the farm. So in addition to myself, the farm manager, I have 3 full-time research technicians that run the day-to-day ins and outs of the farm. So, we take care of a significant percentage of the planting and harvest. We take care of all of the spray applications around the farm, things like that. So, really a bulk of, the infield data collection is done by researchers, but a lot of the, equipment-heavy stuff is taken care of by the farm staff. So I would say something unique about the farm compared to some other research farms is that we rotate our research and what we call our rotational acres, so what we have in bulk production. And that kind of gives each research plot kind of an even year to level out before we put research back in that plot. So in any given year, we have at least as much rotational crop as we do research crop.
So I have a question and a comment about sensing other than sensors that we're going to talk about in a minute that are on machines and in the soil. There's this thing that we call the Pheno rover that we have out here at Acre, and it has LiDAR, hyperspectral, lots of other imaging, and that can go over the crops, right? And then tell us a little bit about, since we are near the Purdue airport, which is the second busiest airport in the state, UAV flying out here has some particular criteria and such, but there is a lot of it going on.
Yes, we have a wide fleet of UAVs out here at the farm, and we are right on the edge of Purdue Airport's flight pattern. So for the most part, the vast majority of the farm, we're in an okay to fly zone. There's, I think, a couple little corners that we're in a little more restricted airspace. But yeah, we have a lot of people based out of right here behind us at ICSC, the Indiana Corn and Soybean Innovation Center, based out of there, that are doing a variety of different sensing with different UAV platforms. So folks in civil, folks in agronomy, folks in AB, all across the board. So.
Good. And just one more comment just before we transition to other sensors. Behind us, you might see this thing that we call the Gantry. And the Gantry is an ABE-oriented project, but it's certainly crop science-oriented. And the idea of that Gantry is to help in transitioning of the data that you get from unmanned aerial vehicles to on-the-ground, ground truth data. So that Gantry, when it's running, scans the crop hundreds of times in a day to determine the effect of sunlight and other climatic factors on what does the imagery really tell you. So it is a translation from things that we can sense in the greenhouse and in the building actually to out in the field. Okay, so I've assembled here what I would refer to as the OTS telematics guru team. So I'm just going to start here with Fabio Castablanco, who's a graduate student in electrical and computer engineering. Andrew Baumos, who is a software and data engineer in the College of Ag at Purdue. Zach Neal, who is an undergraduate student in electrical and computer engineering. And Gaganpreet Hundal, who is a graduate student in computer and information technology. Andrew is my go-to guy on many things, hardware and software. So I'm going to let him talk through some of the sensoring that we're doing on machines, in the soil, amidst the plants, and things like that. We are holding the props. Andrew, what's going on out here at Acre?
Okay, we've got a lot of things going on here. Like you said, we're sensing machines. We're also doing a lot of sensors in the field. So I passed out a sheet here. If you're got your phone, you can go ahead and scan these QR codes. You can see some of these dashboards live if you're interested. And I'll just talk through them. There's some screenshots as they look like this morning, but these are public and you can look at them offline too later if you want. But just kind of starting with LoRaWAN and what we've been doing with in-field sensing. Ag IT has gone through a lot of trouble to get a LoRaWAN gateway. You may not be able to see it, but there's a tower right in the background there. And that covers all of Acre. Actually, we did some testing and we got about 6 miles away and still had a decent connection in some areas. So it's a pretty wide range coverage. And we've put these sensors in the field. They're soil moisture, soil temperature, atmospheric temperature, pressure, things like that. These sort of the data you might need to make decisions on, can I get out in the field today? Or do I need to turn the irrigator on or not? And things like that. And so they're behind us, hidden in this field. If you look carefully, you might be able to spot one here. We can get up and get a closer look in a little bit. They report back once a minute, but they can be turned down to report back much slower. Since we're trying to do some research, we have them sort of turned up a little bit faster just to get see that full high fidelity data. And we can start answering the questions like, how fast should you update if you want to make some of these decisions? Is once an hour good enough? Is once a day good enough? And so on. And all this data flows back to a tool or through a thing called ChirpStack and then back to a program called ThingsBoard. And it makes all the data available live. You can easily plot it, manipulate it, kind of zoom in and out and make different charts. And that's been very helpful because it allows us to come out here and do some of this technical installation and getting the communication working and then handing it off to the more ag engineers who want to do something with the data but don't want to get bogged down with what's a Linux machine and how do I run that command, right? So it's been a nice tool to sort of bridge the two educational backgrounds. And then the other thing that we're doing primarily out here is ISOBlue. This is machine telematics. It's totally open source and it's built on hardware that's just commercial and off the shelf. And we've got a couple of generations here. This one over here is what we kind of call ISOBlue. It's the standard, we call it ISOBlue 2.0. It's sort of the standard one that we deploy in most machines. It connects to the machine's CAN bus, turns on and off with the machine. We can capture the entire CAN log. We can stream it to the cloud if we want. We can do processing on board, so we can pre-process it on the edge, send up just insights. And then it's got it's cellular backhaul, Wi-Fi backhaul, and then we're working on doing things like make LoRaWAN gateways in it, making it a LoRaWAN client, so they might be able to put up positions over LoRaWAN rather than expensive cell. Or where we find in some of the areas we deploy them, not so much here in Indiana, but in some other locations where there is just no cell. And we have to find a different strategy. And then version number 2 This one came off a combine last season and it was mounted outside, so you can't quite see inside. It's different hardware, but it's running exactly the same software. And that's one of the big things about ISOBlue. We really work on the software and not the hardware. And we call the software stack Avana. It's entirely open source and it's really not dependent on the hardware below it, except for that you run Linux. And if you want to put it in a machine, then you need like CAN hardware and things like that. But as long as it's a single board computer that runs Linux, you can kind of put our stack on top of it and you have this sort of working telematics box. This guy, we put on an actual Intel machine. It's a lot more powerful processing wise. We hooked up Wi-Fi APs to them, installed them on a bunch of machines, grain carts, combines, and semis. And we did some in-field networking, so machine-to-machine network, just with off-the-shelf commercial Wi-Fi, and got hundreds of megabits a second most of the time. You could easily stream videos across from machine to machine. You can easily move all the data that the machine's collecting. So in a harvest operation where you kind of have a ballet of equipment moving around, having them being able to communicate, remove some of the burden on the operators, and you can try to hopefully reduce some of the phone call conversations while steering the combine to more like just alerts or things you need to know right in front of you. And then lastly, over here we have ISOBlue Lite, although it may not be called that anymore because this is the brand new version. It's actually been on a machine only once. And when we're done here, we're gonna go put it on a machine, hopefully, if Rachel tells us we can today, or we're gonna do it tomorrow. This is built on a Raspberry Pi, using nothing but commercially available capes, or hats, I believe they call them. And the advantage of it is it's a lot cheaper. What are we at, Fabio? $1,200? Yeah. And keep in mind, that's a research thing. It could be made cheaper. We oftentimes trade ease for cost sometimes, right? This guy, total $200 to $300. They achieve the exact same functionality. This is sort of obviously Rev 2, but we did some speed testing on the hardware, and this guy actually ends up being able to compute better than that one. Granted, that one is 5 or 6 years old now. Yeah. So this is actually probably not ISOBlue Lite, it's ISOBlue now, but that's... So Zach here spent the summer. He took our stack, our existing code. It was a little bit of a test. Can Avana as software just to be deployed on brand new hardware? And for the most part, the answer is yes. Yeah. And then the part that wasn't, we're fixing. And then the last thing I skipped over, this is a LoRaWAN device. Although it's kind of machine related, this is a GPS tracker. It doesn't do any logging at all. It only reports the GPS. So if you don't have LoRa connectivity at the moment, then you lose the position. But when you've got LoRa covering 6-mile range, for the most part, you're gonna have LoRa, when you're on the farm. And so it's a good tool for like machine tracking, or it's got a lot of functionality like I'll report when I stop moving. So you can have this nice feature of where did I leave the bin? Or where did I leave the anhydrous tank, right? Instead of going around and trying to find it, you can just check. And because it only transmits, say, when it stops, this thing will last on the battery for years and years and years, because it's not really transmitting that often, it's just when you move it. What we're using it for now, and we're just about to deploy a whole bunch more, is machine tracking. So during a harvest, just where is everyone? Where have they gone? What are they doing? You can learn a lot if you know a little bit about farming. You know the month, you know what the crop probably is in the area. If there was a machine, you went back and forth at a couple miles an hour and it's spring, you probably planted it. So you can kind of deduce that pretty quickly without a lot of work, and you don't need fancy technology. This is just a GPS tracker. So one of the primary uses of ISOBlue is to get those logs. Here's a different, sort of much cheaper, easier to deploy way. My primary goal in this work is more studying the connectivity. So how well does LoRaWAN work? Is LoRaWAN a solution for ag? And if it is, what are the applications that make sense? And so by doing that, we've deployed sort of kind of commercial hardware. ISOBlue is a little different. We created that, and that's sort of a different project. But for LoRaWAN, for me, it's mostly about the connectivity there. But we are deploying sort of commercial tools, and so we can report at least on those and how on what our impacts are. And then that project is associated with the WHIN project, and they're doing a lot of work with sort of testing industrial solutions, and so we kind of overlap in that a little bit. But
our goal is to get exactly to that. So I wouldn't say that we do yet but we certainly want to. And that's a good question that launches me into mention something that I failed to mention, is that this is sort of becoming a test bed with multiple dimensions to it. Of course, Rachel referred to the agronomy research that's happening, which was the origination. But then as a result of the WHIN, the Wabash Heartland Innovation Network project, there is the WHIN Manufacturing, WHIN Sensors, there is WHIN Ag, which is sort of why, in part, why we are here. There also is funded this project called the IoT for Ag, which is an engineering research center funded by the National Science Foundation. It's in combination with, it's led by the University of Pennsylvania, which doesn't have an ag department. But the strong partners are Purdue University, the University of Florida, and the University of California at Merced. And so that team is looking at 3 different thrusts related to this work that we're talking about. One thrust has to do with specifically communication technologies. The other thrust is sensors. And the third thrust is the agricultural response, or the decision making that you would make based on sensors and information that flows through assorted communication channels. So it's kind of hard to separate what we're doing here. Is it this or is it that? It's usually generally the same people wearing a different hat. And we're here as part of this thing that we call the Open Ag Technology and Systems Center, which is an industry-supported, Foundation for Food and Ag Research supported open source center to bring these open source technologies to farmers, to ag industry. We're not in a position to deploy and support, but what we want to do is prove the technology so that then a startup or a big business can pick it up from there and make it commercial, make it viable for the masses.
Everything you see here, from LoRaWAN, except for the hardware, like the actual device and the actual physical gateway installed, all of the software, to the plots you see in your hands, it's all open source code, either created by us or created by other great people in the community. But everything in this pipeline is deployable by you if you wanted to, but most importantly, sort of interoperable because of the openness, right? You have a good stake in the ground now to demand that the systems work with this because it's already there and it's well documented. I forgot to mention, we also have Wi-Fi out at Acre. And Ed's over here offline if we can answer some questions if you have any. What's it? Yeah, but I think really all to say is that Acre is pretty much covered in Wi-Fi, which is sort of unique, for most farms. The signal quality is pretty good, and I don't want to misspeak, but if you're out here, and I think people are using it primarily as sort of you're in the field doing research and you need to look at stuff, or you want to record things, or be connected to the internet somehow. Did you have anything you want to say on that? Or?
So let me make a quick introduction. This is Ed Stanich. He's in our Department of Ag Information Technology. Yep. He supports not just this farm, but actually several research farms around the state. Yeah, and maybe you can even refer to the Purdue Ag Centers there. Yeah. But Ed, it's you and your team that support the connectivity out here. So tell us how it works, how well it works. You can be honest.
Yeah. All right. So to start out with, we have 2 pairs of fiber that come out here, both in separate paths that come into the Beck building over there, into the telecom room. Each one is lit at 10 gigabits per second, so we have a total of 20 gigabits of aggregate out here. From Beck, we run out on 52 up to 231 to animal science. We provide the fiber for animal science in a majority of the buildings for animal science. From Beck, we run to the grain leg fiber. On top of the grain leg, we have ubiquity radios and antennas that point to a lot of the buildings that are over here. We provide point-to-point to those buildings. Within those buildings, we provide wireless coverage or wired coverage. From Beck, we have fiber out to you can see what we call the weather tower out there. We also have fiber out to 2 other towers that we put up. Both the towers farther north are approximately 60 feet. On top of those towers, there's 3 towers at 60 feet. We have Aruba HP E-Gear. That is what the Wi-Fi is. Covers about 90% of the area. Currently, authentication is done through a Radius server back on campus. What's nice is all of this is Purdue IP space, so that authentication is easy and we can do all sorts of stuff. So what we've done out here, now that we've got all this coverage, what we run into is if people work inside canopies that are dense, the Wi-Fi doesn't work. So we've come up with a couple of solutions. One is which people can get a AP unit like the one that is up there on the Gantry, and it connects to the mesh network, and we provide basically a local hotspot. We can do that with solar or just straight 12-volt battery or whatever. You know, you can bring a truck up, hook your stuff up, and you've got instant hotspot to do the stuff deep inside the canopy that the towers don't get to. Purdue Ag Centers, there's 8 across the state. We provide either fiber or some other commodity network to each of those. And I would say at this point we've got LoRa at 2, Kirby, right? TPAC, and essentially, the mobile up at Rice. So interesting, when we were doing the Wi-Fi, we had all sorts of interesting suggestions, like from putting, going to auction and getting these lift trucks and sticking these lift trucks all around, to doing a balloon. We actually looked at doing, putting towers up, you know, like 100-foot towers, and then having things fly across like at football games, having the Wi-Fi go where it's needed. All sorts of interesting stuff. We set it from the manufacturer, and if we need to, we bump it up as much as we can. And honestly, we found, depending on how we do it, sometimes we have to cut back because it's just the way the cone is and stuff. It just interacts so much with the humidity coming off the crops that if we try to max it out, it just starts bouncing. You know, like I said, we've looked at a whole bunch of different things out here. We actually looked at microwave. There's like a cellular light, which is I think around 4.5, 4.3, that they've deployed at some of the locations down south that I've worked with to get through deep forest to do point-to-point, just basically ISPs type stuff. But it works out pretty well, but nothing with that.
So, like, follow up kind of both those questions a little bit. You know, one of the cool things we have set up here is that, you know, Ag IT, they provide us sort of, I don't want to say commercial, but the standard, you know, connectivity, and they make it work so that when we're out here doing the research that's on the data, like the sensors, I don't care about the backhaul, I just need the data. Yeah. Then we have something to rely on. But at the same time, we also have a lot of ability to come out here and do radio research. And so like Oates, the center that we're from, there's a lot of electrical engineering. Actually, I'm an electrical engineer. And we do, some of us do radio research. So things like bringing TV white space out here or CBRS radios and trying to say, what should the waveform be, you know, for ag? That's definitely work that's starting to happen.
Way over there, we've got the high-powered lines. It actually runs through the north part, and we've done some unique testing through that part of the field because those wires really wreak havoc with everything. Oh yeah, I mean it's kind of interesting. Yeah, like, ooh.
One of the things that relates to the LoRa, these guys are electrical and computer engineers trying to teach an ag and biological engineer about these communication technologies. I am curious, how many of you know what I mean by ADR, the adaptive data rate? So one day, Andrew gave me a very good lesson on that. And what it causes in terms of you need to be aware of it in order to make LoRa work. So if you could give us like a brief lesson. This is just, I think, one example of, well, in urban settings it just seems to work, but there are challenges that the agricultural community must at least have an awareness of these things or it's going to fail. So give us a quick lesson on adaptive data rate.
Sure. Yeah, so adaptive data rate is of course optional, but it optimizes the power usage of your sensors. So if you're really going to deploy things out there and get the maximum battery life, which is sort of the point of all this, you're going to need to use it. And essentially, because LoRa tries to talk as little as it can, every time it talks, you've used more energy. It's arrived at an ADR algorithm, or adaptive data rate algorithm, that just happens once. You first join the network, there's a back and forth between the gateway and the client. It estimates what the signal strength is, and then the gateway says, use this data rate. And data rate's really important because if, as you make the data rate higher, to send the same data, you talk for much less airtime. What uses the power on most of these sensors, the exception of maybe the GPS one, is the talking, it's the airtime. That's where your energy is being consumed. So if you can send the same data in half the time, you're gonna double your battery life, give or take, right? But where this was sort of created was for the smart city kind of application, right? That's where a lot of this came out of, where I've installed the sensor, I have my gateway, it's a community. Not very often do new neighborhoods get built or a house get torn down. The channel is far from static, right? Because no radio channel is static. But the primary interferers are constant. So you can sort of figure out what's your margin over a week or something. Set the data rate and it should work pretty well forever. But here we are, we have sensors in these fields and when we installed them, the corn wasn't up yet. And now you can't see them anymore. And that corn is mostly water. And you can see it very clear, the signal strength drop as the plants grow. And if you are at a data rate, that plant growing now has brought you below your margin, you don't just have loss, you can't talk to it ever again. And if you can't talk to it, you can't tell it to lower the data rate to be able to talk again, or to increase. Data rate's weird to talk, to make it talk longer so that you can hear it again. And it's gone. You have to go out there and find it and pull the batteries. And I don't know, I know there's one right here, but I can't find it. So it's not an easy task. Did you find it? It's actually spray painted orange, believe it or not. It's actually quite hard to find, even though we've tried to make it easy. So, you know, ag, if it's going to take LoRaWAN in practice, it probably needs a new ADR algorithm, the one that doesn't exist yet, that has a plant awareness. It's like the season changes, the channel changes because the plants grow. So that is an example of research that we're working on, the waveforms or the algorithms, if you will. But
I have like deployed here sensors in this cornfield, and there's 2 sensors in the soybean field. So we are like regularly monitoring the data, especially the data rate and the power consumption and the SNR signal and the RSSI values. And we have seen like significantly less values for the sensors that are down there, like near the ground. And we have the sensors that have orientation up on the pole. So with the, just like with the sensors that are near the ground, they are facing like more interference from the canopy. So that is like something that we notice. And like we have also did some like range testing, like short form of range testing with the sensors, like this GPS trackers, to test the range around the LoRaWAN network we have here. And like the idea that you're talking about, the cognitive radio kind of idea, it's pretty much like applicable here in the agriculture. So like figuring out how these all variables relate to each other is an interesting study.
You're going to do cognitive radio and say it's going to be an ag, and the problem is the plant. And I have simple GPS tracks from early in the season when the LoRa was fine, and I know kind of my plan. I know that field's corn versus soybean versus whatever. I can set my margins differently. So it doesn't even have to be cognitive that I'm sensing. It could just be some metadata that you know about what you did on the farm. And that could all happen automatically, you know, if we get there.
So it's great to have you out here at the Agronomy Center for Research and Education. That gives you a glimpse of sort of a combination of sensor research, communications research, but always tied to the agriculture that we're trying to develop and improve.